Don't get me wrong, I love the feeling of a clean workspace after I complete a project, but this happens to me every single time. Anytime I clean up after prototyping or finishing a project, I find resistors like this all over the floor. That's where that resistor went. But I can't be bothered with figuring out what value it is so that I can sort that resistor right then and there. So what I end up doing is actually just throwing it into a bin of resistors like this. And this resistor will stay in here unsorted until now because I've actually never sorted this bin of resistors. And for those of you who are wondering, the answer is yes. I do the exact same thing with machine screws. They all end up unsorted in this bin here. Which means there's only one reasonable thing for me to do. My name is Zach and I'm the Byte Sized Engineer. In this video, I'm going to over-engineer a solution to this problem using the new Arduino Uno Q. The reason I don't sort these resistors in the moment is simple. Each resistor has a set of colored bands that help you determine what value it is. I know there are some of you watching who can pick up any resistor, look at it for a second, and figure out exactly what value it is, but I am not one of those people. No matter how hard I try, I cannot memorize the resistor color chart. There are a couple of common ones that I do recognize, like 1K, 10K, and 100K, but beyond that, I'm at a total loss. Fortunately, there are some good resources out there like the resistor color code calculator on DigiKey's website. But even with these tools, I'm still really slow. Watch. This one is yellow, purple, brown. Well, actually, first it's a tolerance of gold, which is 5%. So yellow, purple, brown. So that is a 470 ohm resistor. But that took me like 15 or 20 seconds. If you multiply that across hundreds of resistors, it's a big task. That got me thinking, what if there was a way to use the Arduino Uno Q to speed up this process dramatically? This board brings some serious capability to the classic Arduino Uno form factor. Most notably is that it has both a microcontroller and a microprocessor that can run Linux. That means it has enough processing power to do machine learning and AI. Let me show you what I'm talking about. I've connected the Arduino Uno Q to a USB-C power delivery hub, which then gets powered by a wall adapter. The example I want to show you requires a USB camera, so I'm going to go ahead and plug that in. Once the Uno Q is fully booted up, I can access it over my network using the Arduino App Lab on my desktop computer. I just double-click on the Arduino Q in the App Lab, and I enter in my password, and then I'll be connected. Check out how many examples there are. If I read through the descriptions here, I found one that says, this example showcases object detection within a live feed from a USB camera. That sounds like exactly what I'm trying to do, so let's load that example. Then I can look at the Python console and I can see that our application is available on this IP address. So let's head back over to the workbench and I'll pull that web page up on my phone. The example is running on the Uno Q, I've got the webcam plugged into it, and I've got the web page open on my phone. Let's see what this can detect. Right away, I noticed that it has no problem detecting me as a person with high confidence. I'm glad that I look normal enough that it thinks I'm a person. I can also see that it detects the fire extinguisher, although it's calling it a bottle, which is pretty close. Let's see if I put a cup in front of it, what does it say? There we go, for a second I had it. All right, it's not doing a great job detecting this cup. What if I do a clear glass? There we go, now it's saying cup. And what happens if I put a plant in front of it? Oh, well, it thinks that the base is a cup. Keep in mind, this wasn't specifically designed to detect these objects. This is just what it sees, what it's been trained on, and it's identifying those objects based on its training. Now let's try putting some tools in front of it, like a hammer. Yeah, it doesn't know what that is. This example is really just for generic object detection. If I want it to be able to detect things very specifically, I need to train a model and then load it onto the board. So I started going down that route. I took a whole bunch of pictures of resistors and I uploaded them to a machine learning training service. Training an AI model is something I have never done before and I couldn't really get it to work reliably. So I reached out to Sean Himmel. He told me that using AI and machine learning to detect the color bands on a resistor is a much more difficult problem than I originally anticipated. So I think I'm going to switch over to using openCV, which is the computer vision module for Python. I used openCV a few years ago when I modified my 3D printer to solve Sudoku puzzles by itself, so I have a little bit of experience to draw from. AI is kind of overkill for this problem. Resistor color bands are high contrast, repetitive, and structured, so this becomes a classic computer vision problem. And luckily, the Arduino Uno Q is running Linux and it has a USB camera plugged into it, so I can just use openCV. I've got a mouse, a keyboard, and a monitor plugged into the Arduino Q. The first step is always the same. Let's get a clean live feed from the USB camera. With just a few lines of code, I can open up a camera object and then capture frames repeatedly. So let's run this script and see what it does. A nice window pops up and we get a live feed from the USB camera. Everything after this is just applying math to these pixels. Before we can start detecting colors, we need to change how this image is represented. The first step in most computer vision projects is applying a Gaussian blur. Blurring an image smooths out a lot of the noise and it will remove a lot of the texture so that we don't mistake tiny details for color bands. Another useful step in computer vision is to convert to grayscale. By removing all of the color information, it's often easier to detect what's in your image. And finally, we can convert these pixels from RGB into HSV. That's hue, saturation, and value. Converting the image to HSV will make our lives easier later on when we want to separate color and brightness. Let's add these changes to the code and see what it looks like. Here we create a Gaussian blurred image. The HSV and grayscale images are just basically a color conversion. Then I'll just show those windows like we did before. In the top left, we have the original image. In the top right, we have the blurred image. In the bottom left, we have the grayscale. And in the bottom right, we have HSV. Once the image is pre-processed, the next step is to create a mask. A mask is just a black and white image where the white pixels are the things we care about and all the black pixels are ignored. Dark resistor color bands don't have a lot of color. They're mostly defined by brightness, so grayscale works really well here. I'm also running into another limitation. It's this webcam. I'm not going to be able to see enough detail with the lens that is on this webcam, so I need to switch over to a USB microscope. And that's exactly what this is. This is just a USB webcam, but it has the right lens on there to look really closely at small details. So let's disconnect the webcam and plug in the microscope. To create the dark colors mask, I just added these two lines of code, and because I don't want to guess at the threshold value, I added a slider, which will make it really easy to adjust. So let's run this code with the microscope and see what happens. Again, we have our original image on the left, and then the right-hand side is the dark colors mask. But before we move forward, I want to make sure that our background is nice and clean, so I actually have a purple post-it note that I'm going to stick down, and that's going to act as our background for the rest of this project. Now I'm going to stick a resistor under the microscope. See how much better that is than the webcam? This is going to give us so much more detail. Now let's look at the dark colors mask. We can see that some of the pixels have turned white. If I match them up with the resistor on the left, I can see that this is the green band. Brown doesn't really show up. The red band sort of shows up and the gold band sort of shows up. Now we start to see one of the issues I have with this setup. The light from the microscope LED is casting a huge glare down the center of the resistor, so it's kind of splitting those color bands into an upper half and a lower half. I'm gonna have to deal with that later on. But for now, let's just ignore that and adjust the threshold value. Now I'm getting all sorts of colors, and as I go higher and higher, more and more of the pixels are allowed through the mask and they turn white. So this is not useful at this point, so I'm going to back down the threshold until I just see the color bands. So somewhere around there is a really good starting point for creating a mask for just the color bands. But let's try a resistor that has a white band. No matter how much I adjust this dark color threshold, that white is being ignored entirely. So we need to come up with something different. Hue, saturation, and value lets us define a color as a range. If a pixel falls within that range, it will turn white in our mask. With these few lines of code, I've created a light colors mask that only allow colors with certain hue, saturation, and value. And again, because I don't want to guess what these are, I've created sliders to help us fine-tune those values. Let's run that code to see what it looks like. And once again, the upper left hand is our original image, and the right hand is the light colors mask. At first glance, this looks just like the dark colors mask. I'm seeing the gold band, brown, and the red band, but I'm not seeing that white color band. So let's adjust these hue, saturation, and values until we get just the white band. I had to do a bunch of research on color theory for this project, and I learned that whites and silvers really are just defined by being low saturation. So if I bring this S max value down, I can see that I can start isolating that white color band quite cleanly. So now we have a dark colors mask, a light colors mask, and we can combine those two using a bitwise OR operation to make one unified mask. At this point, we can see all the color bands, but we need to convert them into data. openCV uses something called contours. A contour is just the outline of one of the white regions in our mask. Once I establish the contours, we can start answering questions like, how many bands do we have? What order are they? And what color do they appear? These two lines of code find the contours, and then these two lines of code draw the contours onto our image. So let's go ahead and run this code to see what our contours look like. From left to right, we have our original image, our dark contours, and our light contours. And I have a whole bunch of sliders to adjust the values to get these to look just right. So let's focus our attention on the dark contours. Right now, we're getting kind of small contours on the top and bottom of the bands. So let's see if we can adjust this threshold to maximize the size of those contours. But I don't want to drag it too far because then I get other bits of the image that I don't want. So somewhere in this area looks good to me. Again, later on, I'm gonna have to deal with the fact that I've got two contours that belong to the same color band. Now let's focus our attention on the light contours. Our goal for this is to be able to draw a contour around the white and silver bands. I know that the white and silver colors are going to have really low saturation, and at low saturations, hue is kind of meaningless. So I'm gonna leave the hue set just as it is, and it will accept the full range. So I'm gonna bring my saturation minimum all the way down to 0, and then the saturation maximum, I'm gonna cap it really low until I can get just that white color band. So somewhere around there looks pretty good. You can see that we've masked out all the other colors. The only thing we're left with in the original image is that white or silver band, and then the really high intensity glare that we see on the resistor leads. This is getting really exciting. The processing pipeline goes something like this. Capture an image, then pre-process it by blurring it and converting it to grayscale and HSV. The next step is to isolate the dark bands, and then we isolate the light bands. And then once we've done that, we can create contours so that we can mathematically approach the next step. Notice how there is no AI involved in this at all. There's no training data. This is just simple computer vision. Now we get to dive into the exciting part or the absolutely terrible part, depending on your tolerance for programming and debugging. If I have all of my masking correct, there shouldn't be that many contours to deal with, but we're going to have small little artifacts that pop up here and there. So we need to sort all of the contours by their area, and that's pretty easy to do with a built-in function. Remember earlier when I said there was a couple of problems that we need to deal with? Well, now is that time. The first one I mentioned was having two contours on the same color band. Once we have the contour sorted, we can find their X position, and if they're not that far off of each other, we can just pick the bigger one and ignore the other. The other problem I mentioned is that we are getting contours around the shiny glare around the resistor leads. That's a pretty simple problem to solve because we can just take the contour width and the contour height and make that an aspect ratio. If it's a really wide aspect ratio, we can just ignore those. Now that I've filtered out all of the unwanted contours, I'm getting pretty solid data here on the color bands. I've got 4 contours being shown at all times, and I've drawn blue bounding boxes around each contour. The next step was actually pretty simple. All I needed to do was analyze the color inside each of those bounding boxes, and I've printed out the hue, saturation, and value for each bounding box. This is getting really juicy because those HSV values are the color of those bands. All I have to do now is just add some logic to sort out those colors and then map those to the resistor values. We're getting super close here and I'm getting really excited. I'm a little bit nervous, but I'm also really excited because I'm ready to test this thing out. I've got a pile of resistors here that need to be sorted into the correct compartment in my bin. So let's dive in and I'll grab the first resistor and see if I can analyze the value. Red, violet, yellow, that's 270K. Let's check that with a resistor chart. That's the right value, so this is working. All right, next one. Brown, black, blue. That is 10 mega ohms. I think that's correct. I got it. All right, we're 2 for 2. Third one. This one I do recognize, so if I can't get this right. That's brown, black, red, that's 1K. That's one of the ones I knew. Okay, 3 for 3. Let's go for number 4. 470K. Let's confirm that. That's it, that's correct. Okay, final one. Yellow, violet, black. That's 47 ohms, and I think that's correct just based on the multiplier. Yep, that's the correct value. So this is working pretty well. Now I'm actually kind of excited to go through the rest of this box and sort these individually. I'm just scratching the surface of what this can do. I think it would be really cool to extend this to my machine screws so that I can sort them by their diameter as well as their length. And of course, since this is running on the Arduino Uno Q, which has the microcontroller in addition to the microprocessor, that means I could add servo motors or other hardware to actually physically sort the resistors when I'm done, which would be a really cool thing to add in the future. If you have some ideas on how I can improve this, I would love to hear about it in the comments. My name is Zach, I'm the Byte Sized Engineer. Thank you for watching, and I'll see you next time.